Now we're going to talk about some refinements to the Flageolet-Martin PCSA cardinality estimation algorithm that are really quite amazing, with a really stunning end of the story, or near end of the story. So the thing to think about is that we want to carefully count bits in order to improve our space-time trade-offs. So let's think about the quantities that mattered in the analysis of this algorithm. We have the number of items in the data stream. And then log base 2 of n is the number of bits that you need to talk about numbers less than n in binary. So that's obviously some sort of bound on how well we can do. But log n, if you take the log of that, it's the number of bits needed to represent numbers less than log n in binary. So, right, because it's just 2 to that power, that's your number of bits. So for most applications, we're going to think of n as being less than 2 to the 64th. And if you don't want to think that, say 2 to the 128 and the same argument holds. So that means that log n is less than 64, and log n is less than 7. So log n, it's almost fair to think of it as a constant. Now, in the typical implementations that we're talking about for probabilistic counting with stochastic averaging and practical deployments, it could use, for the parameter m, you need log n bits. So we use 64-bit words because we want to take advantage of machine language efficiencies. So with m equals 64, it's 64 times 64 bits to get 10% accuracy. Or if it's m equals 1024, it's 64 times m. So that's the key to the number of bits used by the algorithms. So in understanding or thinking about these quantities in this way is really going to be helpful in appreciating the effectiveness and the improvements that we're going to talk about, which are really very simple in the end. Now, as I mentioned, the theoretical computer science community seized onto this problem after a very influential paper by Alon Matthias and Szigeti called The Space Complexity of Approximating the Frequency Moments in 1996. They studied other things, not just the cardinality estimation, but also estimating higher moments. And they formalized the idea of this as a randomized algorithm within the theoretical context of the time. And actually it won a prize, a best paper, for foundational contribution in this field. And their theorem, again paraphrased to fit in with what we're talking about, said that, well, if you use something called strongly universal hashing, then probabilistic counting uses log n bits and is accurate to a factor of c with probability at least 2 over c. So that's a kind of a standard way in the theory community of stating results of this sort. So kind of strongly universal hashing, it's kind of replacing the uniform hashing assumption with the assumption that random bits exist, and we can use those random bits to get better properties of our hash functions. And again, that's the basis for also solving other problems like estimating higher moments and so forth. But the thing is, this paper had a big impact on the theory community, but it didn't have any impact on cardinality estimation in practice. The algorithm just said, well, you ought to use strongly universal hashing, but practitioners are not going to use strongly universal hashing in a case like this because it's way too expensive. And the other thing is the accuracy estimate that they prove is just way too weak to be useful at all, and there's no validation. Nobody implemented this and tested it on any kind of data at all. So with no validation, it's not going to have any impact in practice. So it leaves the practical programmer just wondering what to do. That person's still going to use PCSA. There is an interesting quote from this paper where they say, Flageolet and Martin assume that one may use in the algorithm an explicit family of hash functions which exhibits some ideal random properties. Since we are not aware of the existence of such a family of hash functions, and then it goes on. And that's not what they did. What Flageolet and Martin said, that was a thought experiment. If you had this, then certain properties would ensue, but they addressed that thought experiment, implemented it with stochastic averaging. And the other thing they did was they hypothesized that the hash functions that were used in practice would be as effective as the ideal ones that the theoreticians would want. And then they validated the hypothesis by proving tight bounds that match experimental results. It's really important to understand the different points of view of the researchers when trying to apply results like this in practical applications. So with hashing, in the theory of computing, that uniform hashing assumption is not proved. So how can you do anything with something that's not proved, they think. In the practical computing world, we've been using hashing really successfully for 50, 60 years, and we're going to keep doing it. For analysis of algorithms, what we say is that we've done precise analytic models and we've done extensive experiments, and there's validation. So you can use these methods with confidence. And the same thing is true of random bits. Theoretician starts with the axiom that we have random bits. The practitioner, they don't like random bits, and actually they don't like using randomized algorithms because they want to make sure that they can test and retest and retest, and it's harder to do with randomized algorithms. Again, with analysis of algorithms, we say a more effective path forward is to do precise analysis and validate it. And even if you need stronger assumptions to do the precise analysis, once you have the validation, then you've got a good reason to apply the idea in practice. So things, I'd say, diverge a little bit. There's a paper in 2002, nearly 20 years after PCSA, which improved the space accuracy trade-off a little bit, but required a lot of extra stream processing expense. And it also introduced the idea of using real numbers instead of bit patterns, which is interesting. And their theorem is more like, with strongly universal hashing, there's an algorithm that uses m log n bits. So it goes from log n to log n, again from 64 to 7. And gets relative accuracy, and that's a big O bound. And again, this one didn't really have any impact in practice because, first of all, no one would use it because the stream processing expense is much too high. Second of all, we don't really know what the accuracy is. It's hidden somewhere in the big O notation. And again, no one implemented it and validated it. Maybe you could figure something out if you were to do that. At about the same time, again, that leaves the practical programmer still using PCSA. At about the same time, Flageolet, with a co-author, independent of that previous paper, came up with an algorithm called log-log, which is a very easy variant of PCSA. And it improves that space accuracy trade-off without really any extra expense for value. And they have a full analysis fully validated with experimentation, so it can be deployed. The idea is very simple. Instead of keeping track of little r of x or big R of x for each stream, we keep track of the minimum value seen. So before we were saving a value, a 64-bit value. In this algorithm, we save an bit index into that value. So just the minimum value of little r of x in the stream rather than the whole sketch. And so their theorem is more like this. The log-log algorithm uses m log n bits, and it gets a relative accuracy close to 1.30 square root of m. A very simple change, but again, backed up with full analysis and experimentation. And this algorithm had practical impact. It was deployed for network switches in a telecommunication system. Now we're not going to go into it in detail because an even better idea came along very soon thereafter. And that one's called hyperlog in 2007. And the idea is for this is the same as log, but instead of using the standard arithmetic mean, we're going to use the harmonic mean, which dampens the effect of outliers in the data. So we have been using the standard arithmetic mean, where you just take the values, add them up, divide by n. And the harmonic mean, which has many uses and many applications in similar circumstances, is to do this computation. And this simple example shows why it's helpful. So in this example, we're talking about 31 values that are all equal to 20,000. And then we're going to just have one outlier that varies on the x-axis from 5,000 up to 80,000. So the arithmetic mean, as that outlier gets bigger, its effect on the mean, grows linearly, obviously from the formula. But for the harmonic mean, its effect is less and less as it gets bigger. And that type of effect is well known in many applications. And the idea of hyperlog was to go ahead and use that. And again, there's full analysis and validation that this idea works with specifics, and it means that this algorithm, hyperlog, could be immediately deployed in applications. So here's the code for the hyperlog algorithm, really very tight algorithm, 2, 4, 6, 8 lines of code. It uses stochastic averaging, keeping track of the minimum value of RVEX for each stream, and then computing the harmonic mean. And again, the theorem, again paraphrased as we have been doing, saying if you have uniform hashing assumption, we use m log n bits, and we get accuracy pretty close to 1 over square root of m. That's a specific constant. That's not a big O result. And again, in the paper, it's validated in lots of experiments. So now the space accuracy trade-off. So again, let's say n is less than 2 to the 64th, which 2 to the 64th is a pretty huge number. And now we get close to 10%, 12% accuracy with just 396 bits. Rather than keeping 64, we keep log of 64, just 6 bits. And if we want to get 3% relative accuracy, we can do it with m equals 1024, again, just 6 bits, 6144 bits. Again, quite amazing that even for a huge stream, n less than 2 to the 64th, with 396 you can get within 12% is really quite amazing. So programmers like that, they can see that result, they can see that 8 lines of code, and they can deploy it in practical systems. So again, in a typical PCSA implementation, we use log n bits. We use 64-bit words to take advantage of the machine language efficiencies, and then we get that kind of accuracy. But for hyperlog, we only need m log n bits. So we can use 8-bit bytes usually to take care of machine language efficiencies. So therefore it's 512 bits to get around 10% accuracy with n less than 2 to the 64. So validation, that's the right answer, hyperlog. And if you answer that, you may not get the job, but you'll get the next part of the interview anyway. And it's a very simple algorithm to explain. For validation, modern internet and computer companies are dealing with huge amounts of data. And there's actually an influential paper published in 2013 that got all kinds of companies to notice that they could get accurate cardinality estimation with using the hyperlog algorithm. This is my favorite. Amazon announces hyperlog. This is 8 lines of code, that was invented 10 years before, and they announced that they have deployed it. They could have discovered it, I think, a long time ago. This algorithm is widely used. And again, it's couldn't be used without the validated mathematical analysis and experimentation that were in the original paper that's so rare in many papers coming out of the theoretical computer science community, but is the bedrock of papers in the analysis of algorithms. So I used to say that Philippe Flageolet, who died unexpectedly in 2011, was a great mathematician and really computer scientist. Not many computer scientists, and he's definitely one of them. But now I like to say he was also a data scientist, starting in 1983, even though recently people are just starting to use this term. And there's a great paper by Jeremy Lombroso, who was Philippe's last student, which gives a lot of information about Philippe's contribution to data streaming algorithms. For much more information about Philippe's pioneering contribution to data streaming algorithms, there's a paper posted by Jeremy Lombroso, Philippe's last student, which gives a lot of the details that we've been talking about.